first group is going to be talking about a system to cancel noise. They're looking at the open field noise cancellation. And the group consists of Adamir, and I'm not sure how to pronounce that, Adamir.
It's Aldemir Shainov.
Aldemir.
Yeah.
But not your last name.
Shainov.
Shainov. That's what I was asking. I tend to use first names, and I apologize if I don't get names exactly right. And Dan Kozlow, I hope that's close. And Yuri, I know quite well. And Denkea, is that Yuri? You here? Maybe not. He's been working with.
Yuri's not here, no.
I know
I think he's moderating.
He's moderating. So Dan, you're going to lead us off and talk about the project?
Yep.
Okay, very good.
All right. Thank you for having us, Dr. Katz. My name is Daniel Kozlow. I have with me Aldemir Shainov, and as we just said, Yuri is busy right now. He wasn't able to be here for this presentation. We've been developing an active noise cancellation system for a fan. So in this presentation, we will discuss this active noise cancellation system. And something to note about it, this is an entirely analog system. There are definitely ways to implement this digitally, but the focus of this was to see how we could do using an entirely analog system. Our circuitry is comprised of three main stages: a bandpass filter, a current and voltage amplifier, and a phase shifting circuit. The circuit takes input from a microphone in close proximity to the fan and outputs sound waves from a speaker to provide destructive interference. So the goal is to use this system for a fan in the workplace. So a small fan that would probably fit onto a desktop. The speaker would be mounted to it to eliminate the hum of the fan. Now, the actual buffeting sound of the wind, that is not something that we'll be able to cancel with this system, but the humming noise, we will hopefully be able to eliminate as much as possible. So the effectiveness of this system will be measured about 2 to 3 feet away from the fan, because as I said previously, this is for more of a workplace environment. It's not going to be in the cafeteria or something. This is for where you want to have a quiet fan to allow you to work in a quiet environment. So in order to measure the effectiveness, we will use a decibel meter, and we'll see what the dBA of the fan is without the noise cancellation and the difference it makes when we have the noise cancellation activated. The interference will be provided using a speaker mounted to the center of the fan, and the system will primarily give cancellation at the center frequency of the fan, which we determined experimentally. And also we will need the audio amplification stage to give a gain of 10 to 15 times to allow for an adequate intensity for the speaker. So here's a quick little block diagram just to show the different stages of the system. We have the fan, which creates the fan noise, and a microphone will pick up that sound and filter out any background noises we want to specifically select for the primary frequency of the fan. And then this signal will be amplified and then phase shifted so that it is as close to 180 degrees out of phase of the original sound as possible. And then a speaker will output that new phase shifted sound, and hopefully the resultant sound wave that reaches the user's ears will be much quieter than without the system. So first we had to experimentally determine the frequency of the fan. So the fan has 3 speeds. However, through most of our testing, we primarily focused on the highest speed of the fan. So we we used our phones to simply record an audio sample of the fan running. And we did a fast Fourier transform to see that the center frequency of the high fan speed was about 102 Hertz, which also lined up with the manufacturer settings that were listed online. So that's going to be the frequency that we designed our filter around. Now, we chose a pretty simple design for our bandpass filter. You could see the characteristic equations on the left that we use to determine the different component values. This is a first order filter, but we added one more filter to the end to get a sharper frequency response. So this is the design that we ended up going with. And here's our simulation results for the bode plot of the filter. And we implemented this physically on a breadboard. You can see here, it just consisted of 2 op amps, 4 capacitors, and a bunch of resistors. And we got this bode plot as a result. Now, in order to get this bode plot from the physical circuit, we had to use the National Instruments virtual bench to, what we did was we used this LabVIEW API software from Texas Instruments that took control of the virtual bench and cycled through all the different frequencies in order to get this gain plot. So this is right about what we wanted. You could see it peaks at right about 102 Hertz. And that's where we want the maximum cancellation, because that's where most of the noise from the fan is.
So this is our audio amplifier design, and it can be split up into 2 stages, the preamp stage and the power stage. And this amplifier is designed to have a variable gain with the use of potentiometer. And right now it's set to have a range between 10 and 15. And this design makes use of feedback to ensure a flatter frequency response. And then I used the 741 op amps, and I also used some power transistors to get effective current gain. I used the TIP31 and TIP32 respectively, and they form a symmetrical push-pull Darlington connection. Yeah, next slide. Yeah, so the results for our amplifier are displayed here with the virtual bench, and then using a test signal at our center frequency for the fan at 102 Hertz, with the potentiometer set to a ratio of 13, we get an effective gain of 13. Moving on, we go to and after we tested our filter and amp and our phase shifter, we implemented them together in Spice to see the results that we would get. In the bottom left, on the bottom left, we have our filter, which flows into the amp, which flows into the phase shifter, which would go directly into the speaker. And this is our frequency response. It shows the gains at different frequency, and we can see at our center frequency around 100 Hertz is when we have the most gain, which is what we want. And we try to ensure that it rolls off and it's flat as possible. And on this graph, we can also see it shows the phase over frequency, and the dotted green line represents the phase shift. And we can also see that is at our center frequency as well.
So where we're at currently, when combining all these different systems, we were able to achieve a small level of noise cancellation for the fan. However, it's not as much as we would like. We have achieved the desired outputs for our phase shifter and bandpass filter, but we need to further calibrate the audio amplifier. We've run into some issues with the transistors actually burning out with the audio amplifier. So we need to work on getting the most out of it as possible without that happening. So using heat sinks and things like that. So that's currently what we're doing. And we're hoping to get a much greater level of noise cancellation. And once we're confident with our audio amplifier and our system works when implemented on the breadboard, we will submit an order for our PCB components. We've spent some time designing the separate boards for the filter, the audio amplifier, and the phase shift. And now we're just working on finalizing that design by doing these breadboard tests. And we should be done with that by the beginning of next week, actually. So that's when our orders will go out. And then while we're waiting for our PCB to come in the mail, we'll be working on mounting the speaker to the center of the fan guard. And then also mounting the microphone somewhere where it's not affected too much by the buffeting noise of the wind, but so that it picks up the humming of the fan only. And there's going to be a lot of trial and error involved in that. So we can't just like screw it on somewhere and hope that it works. So we'll figure out the best way to do that. So yeah, that's where we're at. Any questions? Oh, I see a question in the chat. Does phase and filter also affect cancellation? So yes, it does. The phase and the filter is, there is a phase shift that comes from the filter. So that's why we need to use variable resistor in the phase shifter circuit itself. So yeah, that's going to be something that we'll be able to change on the fly to make sure that it's at the optimal phase shift. Yeah, we tried to get the phase shift to be at 0 at the center frequency for the filter, because we want as little phase shifting to happen in the filter stage. So yeah, that is something that was difficult to work with, but we're feeling good about it now.
Yeah. So Daniel,
Yeah.
you're trying to get rid of the humming sound. Don't you think that has something to do with the supply frequency? So your supply frequency is 60 hertz, right? So you did an experiment, you got something, you said 102 or something like that. So
yes,
I suspect that you are dealing with 60 hertz and the harmonics,
yes,
of 60 hertz.
We got that 102 hertz from doing the fast Fourier transform on the fan noise. Like I said, it was also listed on the manufacturer settings, or sorry, not manufacturer settings. On the manufacturer info online, we were able to find the RPM of the fan, and we just did a little bit of math using the fan blades to calculate what the frequency of the sound would be. And through that research, we actually found that most fans do have like roughly the same RPM because they are running off the same power grid. So that was interesting to find. Yeah, but the manufacturer specifications did match up with our testing.
A quick question from this end. I'm trying to figure out acoustically how it would work if the fan kind of sends out that audio signal in 360 degrees acoustically around the fan, right? So you're canceling it at one point?
Yes, yeah, that's the thing. I believe Dr. Katz mentioned in the beginning that it was open field, but that's not the goal of this actually. This is meant for personal use, like someone at their desk. So you're not using this system, you don't have to worry about other people in the room necessarily. You're just trying to use this for personal use. So yeah.
But is there a risk that the sound will find its way to the listener that is from the other portion of the audio that wasn't canceled in the other direction?
You're right, there is a risk, but from our testing, there was a difference. So yeah, it's not going to be perfect. There's limitations when we're implementing this in an analog system. I feel like we probably could have dealt with that stuff in a digital system, but yeah, you're right. There are limitations to this.
I just wonder if a simple solution might be to have audio surround the fan. In other words, a bunch of amplifiers or speakers catching the signal from everywhere.
Yeah, that would definitely help, actually. Yeah. We do have multiple speakers, multiple microphones, so we could try to implement something like that, but yeah, we didn't initially have that in our plans, so but we could test it out.
Yeah, the FAR, the field, open field is a interesting problem, a difficult problem, as Kevin, you're pointing out there. And I think the idea here by this group and their advisor was to really investigate the problems and what the difficulties are in open field acoustic cancellation. You now have some automobiles that are offering noise cancellation open field. And I don't know if we're limited on time here. So we're a little bit over, though we have some flexibility in this here at the end. So I don't know if you did any research on some of the companies that are offering open field. I guess you just consider this that more, you're going to start off with a more limited problem than they have in the total open field in like an automobile.
Yeah, that's the thing. We are limited because all the suggestions that we've been getting from you, Dr. Katz, and also like in our design showcase last semester, a lot of people were saying, oh, why don't you implement it digitally somehow? Because that would give us a lot more flexibility. But Dr. Woody wanted to keep it much more limited in scope. So that was mostly his decision. But yeah.
So there are applications where analog makes a lot of sense in getting experience in doing it analog wise. Are there any other questions before I cut this, go on to the other group?